Nice to meet you.
Okay, we're going to start up with Mumtaz Aerospace and their design. So it's the same kind of RFP that the previous team had described. So we're going to be looking at a different design now, but the same RFP. And so without any further delay, Shali, I'll turn it over to you, and it's all yours.
Good evening, everyone. We're Mumtaz Aviation, and we're here to present our preliminary design of the Skyclops surveillance UAV. So this is a response to El Paso Natural Gas Company's request for proposal, and I'll start by introducing the team. I'm Shali, the design team lead. We have Isam, our systems engineer. We have Katie working on airframe and as the CAD master. We have Bonus, our aerodynamicist, Kevin, our system performance engineer, and Tyler, our propulsion engineer. Thank you, guys. Next, this is an overview of our aircraft. Our engine is the 3W 80XI, and the wingspan is 14.1 feet. The length of the aircraft is 6 feet. Height is 2.3 feet. Our takeoff weight is 38.9 feet, and our empty weight is 29.8 feet. This is what we'll be talking about today. We'll give you a background about what we've done so far and how we've narrowed down the design space. And then we'll look at the characteristics of our aircraft. We'll present to you the performance assessment and the production plan. Then we'll end with risk assessment, the cost estimations, and a program performance update. First, I'll pass it off to Isam, who will give you the background.
Thank you, Shah. So for statement in need, we have unmanned surveillance aircraft, and we have our mission is to fly 300 miles in 6 hours. And we have the 10% condition, which have density 0.06 pound to foot cube, and we have the pressure 25.3 inch mercury, and we have temperature 86 degrees Fahrenheit. And we have the maximum. We have the maximum takeoff and the landing distance, which is 500 feet. So the surveillance aircraft design is not including the payload. And we have the maximum altitude about 700 feet, and we have the maximum weight 55, and the maximum payload 10 pounds. Design envelope. First column, parameters, description, values, and units. This table is important. It comes from 3 main sections, which is aero, propulsion, and performance system engineer. These tables come from the aero and propulsion system. We have reported number like aspect ratio, which is 15, and cruise speed 72 miles per hour, and stall speed 31.8 pounds. And these tables come from the performance system engineer, and we have important numbers like landing distance, which is 400 feet, and the takeoff distance 290 feet. Constraint analysis. The vertical axis is the power loading, horizontal axis is the wing loading. The blue line is the cruise speed, and the gray line is the maneuver. And the red line is the stall speed. And the point show our flight UAV region. As you can see in the shadow line is the space for our UAV. So concept of operation, this is show our flight departure and the landing point. We're going to take off from Tucson, and the flight will take place at 500 feet AGL, and the flight speed is going to be 72 miles per hour. We're going to have transmitting for a live feed video, and we're going to have a GPS for tracking our UAV. We're going to land in Tucson and El Paso, and we're going to have a CD card for data. So the El Paso Natural Gas Company used the Cessna 172. So we make estimate conversion between our UAV and the Cessna 172. We consider fuel, finance, fixed cost, tires, maintenance, and service. And as you can see, Our UAV is way cheaper than Cessna 172. And now I'm going to pass it to Tyler to talk about the engine and propeller selection.
Thank you, Sam. So, as stated before, we have to fly 300 miles in 6 hours with 75% likelihood occurrence of winds. Assuming that that wind is a headwind, the constant for the entire duration of the flight, we have to cruise at 72 miles an hour airspeed to meet our time requirement. We also must weigh less than 55 pounds as stated before. So when we make our engine selection, we want an engine that has a low fuel consumption during the cruise phase, which is the majority of our flight. We want it to be low cost and lightweight. So initially for our propulsion selection, we did a trade study between electric and gas, and the two options that we compared were the 3W28i and the Rimfire 1.6. They both put out about 2 horsepower at maximum RPM, and just based on weight alone, with just the motor and the batteries, the electric alternative comes out to be 21.5 pounds, while the gas and engine alternative comes out to be 14.1 pounds. With such a tight weight constraint of 55 pounds, we opted for the gas. So after picking the gas, we wanted to investigate other aircraft with similar missions. So we investigated the in-situ Scan Eagle and the UAV factory Penguin B. The in-situ Scan Eagle has a power-to-weight ratio of 0.04 horsepower per pound, and the Penguin B has a power-to-weight ratio of 0.05 horsepower. So for a 55-pound aircraft, which was our maximum weight, we wanted an engine between 2.2 and 2.75 horsepower. So 3W is a very nice manufacturer because they publish all of their data, which is very helpful. So we compared different 3W motors of different displacement to select which one we wanted using a decision matrix. We evaluated them with the criteria shown and gave them a rating between 1 and 10, with 10 being the highest. All criteria were weighted as shown as well, and after normalizing and weighting the data, we found that the 3W28i had the highest figure of merit. However, after consulting Dr. Haven, we were advised to get a thrust-to-weight ratio of 1 for detail, because if we take off and have a low-altitude stall, we want to be able to recover very quickly. So we actually opted for the largest engine, the 80XI. This is the 3W80XI. It is a fuel-injected 2-stroke engine. It weighs 5.51 pounds and puts out a maximum thrust of 38 pounds, static sea level, with 20% installation losses assumed. On the tables previously, there was a number for the aircraft weight of 39 pounds, so we're very close to the 1 thrust-weight ratio. It is also estimated to cost $20,000, so for all of our consideration, we're expected to meet our requirements. The table that is shown is actual engine data from 3W, and it is using a 24 by 10 inch 2-blade propeller. From ERAU, we got the drag to be 7.6 pounds, and we know that for steady level unaccelerated flight, which is the majority of our flight in cruise, our thrust was equal to our drag. So using the equation shown, we calculated the power required of 2.06 horsepower with a 20% installation loss assumed and a 0.85 propeller efficiency. That same data was also plotted because fuel consumption and horsepower are not a linear relationship, so we curve fit the data to get a better estimation for fuel consumption during our flight. As you can see, fuel consumption is the vertical axis and horsepower is horizontal. So we have to take off and climb to 500 feet. We'll be at full power for about 2 minutes, which means we will burn 0.04 gallons of fuel weighing about 0.23 pounds. During our cruise, we used the curve fit, which is the same from the plotted data, and estimated that we will burn 1.66 gallons of fuel weighing 9.94 pounds. After that, when we descend and land, we'll be at idle for about 3 minutes or so, and we will burn 0.01 gallons of fuel weighing 0.03 pounds. So when we actually build the aircraft next semester in detail, we can't spend $20,000 on an engine. So we selected a comparable engine, the VLE-85. We did not use it for the entire design of the aircraft because it is not fuel injected, it has no engine data, and it would be very hard to actually estimate all of the, to see if we meet all of our requirements. It weighs 5.62 pounds, puts out 8.5 horsepower at max power, and costs $550. Next will be Balmas Lopez to talk about wing sizing and aerodynamics.
Thank you, Tyler. So the first characteristic of our wing that we had to choose in order to design it is the airfoil. First, we had to compare different airfoils that we thought were easy to build. This means that they had a relatively high thickness. And we compared them in X-Plotter 5. From this comparison, we wanted a low drag profile, as well as a combination of a high lift. From this comparison, we decided to choose the NACA 4316. But after finding out that we didn't have enough data for this airfoil, we had to go back into NACA report 460 and we found data for an airfoil that was very close to it, the NACA 4315. So this is the airfoil that we used for our wing. Here are shown some of its lift and drag characteristics. On the left, we have the lift coefficient axis, which corresponds to the red line. And on the right, we have the drag coefficient axis, which corresponds to the blue line. They both share the horizontal axis, which is for the angle of attack. You can see how in the lift characteristics of the red line, since our airfoil has some camber, the angle of zero lift starts at about -4 degrees. It also has a CL max of about 1.55 at a stall angle of 19 degrees. Also notice how the stall region is pretty lenient, which is what is a desired characteristic for our airfoil. Also for our drag, notice how at low values of CL we stay low, which is a characteristic that we want because that's where most of our cruise flight is going to happen at. So in order to select the rest of the parameters of the wing, we had to follow decision matrices. In this case, we are comparing different aspect ratios, and the aspect ratio with the highest figure of merit is the aspect ratio 15. Therefore, it was chosen for our design. Now on the screen, you can see all the parameters of the wing as it stands right now. First, from getting a wing loading from systems engineering of 2.97 pounds per foot squared, which would have given us a 5% margin from our design point. We started, and with the aspect ratio of 15, we were able to calculate our wingspan of 14.1 feet. After that, by using also decision matrices, we were able to choose a taper ratio of 0.5. which would make our root chord longer, which would make it easier for us to implement structures at the root. Also notice how the tip, since it gets skinnier, the weight at the tips is less, and the thickness at the tips the thickness difference is less, which means that our drag due to vortices will be decreased. Also, after getting all these parameters, we were deciding if we wanted any dihedral or sweep band. But since that would complicate our structures, we decided not to implement this into our design. So for this wing configuration, we have a wing area of 13.3 feet squared, which would give us a 6.6% margin for our design. And the oscillator efficiency factor, represented as an E, is 94%. The closer it gets to 100%, the closest the lift distribution is to an elliptical lift distribution, which is the ideal lift distribution. And if we have a close lift distribution to an elliptical lift distribution, we have reduced drag due to induced drag. So, after having considered the lift that was produced by the horizontal tail and the body of the aircraft, we were able to come up to estimate this lift curve. You can see the design point is about 0.3 lift coefficient, which lies at about 0 degrees of alpha, so we won't need any incidence angle in our wing. Also notice how most of the characteristics of this lift curve are taken from the airfoil of the wing. That's why the selection of the airfoil is so important. And by using using, by the way, this was estimated by using Wigner and Brand methods. Also, our cell angle is predicted to be at about 19 degrees, and our seal max of about 1.52. And then from Roscom methods, we were able to determine the drag coefficient for each of the components of the aircraft, and we were able to estimate this curve. Again, the circle there is where about the sign point of a CL of 0.3 would occur. We stay low, which is what we want for our cruise conditions. And we would not surpass a 0.06 drag coefficient at that point. Next, we have the pitching moment. This is we can quantify how stable the plane is going to be longitudinally, so in pitch. So we need our pitching moment to be 0 at about the sign point of 0.3. You can see that we cross at about 0.3 with an incidence angle on the horizontal of about negative 0.3 degrees. Though we will not be implementing this in our details phase because it's such a small margin that we won't be able to implement that. So we will try to implement it with a 0 incidence angle and to enter in flight. Also, notice how the slope is negative. That means that we're stable. And with the slope of that graph, we were able to calculate the static margin. If we divide the slope of the pitching moment graph by the slope of the lift curve, we will be able to calculate static margin. This is also a quantity that tells us how stable we are longitudinally, and it ranges between 15 to 25%. And we lie in the stable region. And you notice that we do have 2 static margin percentages since our CG changes during flight for takeoff and landing. But this CG changes so slightly that our difference between static margin percentages is just about 0.1%, and we won't have to worry about any stability issues. Next, by using the drag coefficients that we found from Roscom, we were able to determine or estimate the drag force versus the velocity of the aircraft. You can see how on the left side, the induced drag is the one that dominates, and the right side is the precedent drag where it dominates. And our design point of 72 miles an hour, the drag is predicted to be 7.6 pounds. Lastly, we were able to estimate the efficiency of the whole aircraft by graphing the drag coefficient versus the lift coefficient squared. By obtaining the slope of this graph, we were able to determine our K value, which are the same values. And we used that to estimate our efficiency. So as said before, the efficiency is how close we are to elliptical distribution. And for the whole aircraft, we're estimating an 82% efficiency. So now I'll pass it down to Kevin, who will be talking about tail sizing, performance, and stability control.
Thank you, Bomas. First, I'll be going over tail sizing. The 5 main criteria used for the empennage decision-making process were manufacturability, weight, structural rigidity, yaw authority, and pitch authority. For the preliminary design phase, the inverted U-tail was chosen because it had the highest degree of merit. However, based on experiences and recommendations from previous groups, for the detail phase where we'll actually be building this aircraft, the tail may be reconfigured to the A-tail for its ease of manufacturing, as well as the reduction in weight and drag. Using the tail volume coefficient method, the initial tail surface area is calculated. Raymer suggests that for a single propeller general aviation aircraft, the coefficient of 0.04 and 0.5 are as follows, and the calculated surface area are as shown on the slide. Next, I'll go over stability and control. The left table shows the 5 calculated static stabilities compared with typical range for a subsonic aircraft. These were provided by Dr. Bordignon. As long as the aircraft meets those criteria on the far left, the aircraft is statically stable. The only value that is not within the range for a typical subsonic aircraft is CL beta, but that is because for our design, the aircraft has neither wing sweep nor wing dihedral, which are major contributions for CL beta. On the right shows the aileron and rudder deflection coefficients. These were calculated as they are essential in determining the roll and crosswind assessments. Typically, aileron and rudders can deflect up to positive or negative 25 degrees. The roll assessment on top shows that the mil-spec requirement for side slip, which is 10 degrees of side slip, can be met within reasonable deflection angles. Using Simulink to model the roll assessment equation on the bottom, it was observed that the aileron sizing also meets the mil-spec requirement for time to bank, which is it should take at most 1.7 seconds to reach 60 degrees of bank. And now I'll go over mission performance. The figure on top shows the 5 important phases for the aircraft design profile. On the left shows that the aircraft is capable of takeoff and landing within the 500-foot RFP requirement. On the right table shows that the aircraft is also capable of exceeding the 300 miles as well as the 6-hour range endurance requirements. Although there were no RFP requirements for climb and descent phase, these were calculated to complete our aircraft performance. The left table shows the specific excess power the aircraft has at the 3 major operating environments, and the right table shows the descent, the glide characteristics of the aircraft if it were to lose engine power during mid-flight. And now I'll pass it down to Caitlin.
Thank you, Kevin. All right, so initially we wanted to know what the weight of just our airframe was. In order to do that, we had to use the table on the left. That includes our payload weight, our engine weight, and our fuel weight. From this, we could take our total weight, subtract those values, and we get an empty airframe weight of 15.39 pounds. Knowing this empty weight of 15.39 pounds, we were able to calculate the overall aircraft empty weight by adding back the engine weight and the payload weight. This came out to be 29.8 pounds for us. So using the table on the right, it is Rosklin's method. What it does is it normalizes a bunch of historical data and helps us to get an average value for each of the subcomponents of our aircraft. These subcomponents include our fuselage, our wing, our empennage, and our landing gear. So from this table, we use the center values, which are the average values. So knowing the average weights of all of the subcomponents of our aircraft, we're able to get a CG for it. But we also have to take into consideration the location of our payload inside of our fuselage. So we place the heavier components in our payload compartment closer to the front of the aircraft to try to get our CG in the most ideal situation. Our CG for the best static margin would be at 18.25 inches from the nose in the X direction. However, as you can see from point J at the top, our CG lies at 18.5 inches back from the nose. So our CG does change from takeoff to landing. This is mostly because we deplete our fuel inside of our fuel tank. During takeoff, when we are max loaded, our CG is at 18.5 inches from the nose, and once we land and our fuel is depleted from the mission, we're at 18.48 inches from the nose. You can also notice from this table that our YCG stays at 0. That's because we've lined up all of our payload components on the center line of the aircraft to eliminate that component of CG. It can also be noted that our ZCG goes from being above the center line of the aircraft to below it as we deplete fuel. The next step that we took was deciding how our landing gears would be configured. We decided to go with a tri-scope gear since we do have an aft-mounted engine in order to keep our prop up and away from the ground. So we had to use Rossman's method to determine how far apart our main gear would have to sit and how far our nose gear would have to be from our main gear to meet tip-over criteria. So using that method and assuming that 15% of our total weight could be placed on our nose, we determined that our nose gear would sit about 4.7 inches back from the nose, and our main gear would sit about 20.6 inches back, with a base of 16.3 inches between the main gear. So this is an overlook of our interior structure. It is all going to be made out of plywood. What we have here is 3 formers, a firewall, and 3 platforms to carry our camera, our payload, and our gas tank. It can also be noticed from the picture that all of the joints putting our payload structure together will be made using box joints. This allows for us to translate any loads on the structure in both the X and the Y direction. It also maximizes the surface area for gluing the parts together. So here's our wing. When we manufacture it, it will be broken up into 4 pieces. The 2 wing root sections and 2 outboard wing sections. This will allow us, since we have a 14-foot wingspan, it will allow us to take it apart for easier transportation and storage. As noted by the 2 arrows on the picture, that's where bolts will be located, running through the wing skin and through the spars, allowing us to attach and detach our wing quicker. Much like our wing, our empennage will also be removable from the aircraft. Once again, as denoted by the arrows, 4 bolts or pins will be located in those locations, allowing us to remove the booms and remove the tail from the aircraft. This will allow us to fit within our constraint of the 8-foot truck bed. So now we'll be going over the material selection and the production plan for our aircraft next semester. So we're going to start with the decision matrices. Basically, we looked at 4 different materials, and we determined which one would be the best to make our aircraft out of. Now for this, we assumed that our aircraft would be made out of one singular material for every component of it. Using this, we normalized the data, and we found that the plain weave carbon fiber would be the best to make our aircraft out of. However, this isn't realistic. So we use carbon fiber for only the most important parts of our aircraft, including the booms, landing gear, and the external skin on both our wing and our tail. For the internal of the wing and the tail, we're using foam. We're going to have a fuselage made out of E-glass. This is mainly because carbon fiber does have a tendency to interfere with the radio transmitter system. For the interior structure, as I mentioned before, everything will be made out of plywood. So this is just a flow chart showing our production plan for next semester. Starting at the top left, you can see that we're going to be making our internal plywood structure first. Then moving on to our fuselage, the middle section, which is where the payload component will be stored. Then we're going to move to the cowling and the front portion of the aircraft. Then to our wings, starting with the roots. Since they're going to be permanently mounted to our fuselage, we want to make those first. And then we're going to move to the outer wing sections. From there, we're going to head to the vertical tail and the horizontal tail, attaching them with the booms, and then mounting our engine, mounting our payload, mounting our landing gear, and completing our aircraft. Now I'm going to hand it back to Shali to go over our unit cost and risk mitigation.
So I'll begin with the cost of the production unit. So I use 4 different cost estimation methods, but the DACA model, the RAM4 method, seemed the most comprehensive. We estimated the production unit cost to be $66,300. This includes the camera, the engine, and the research development, testing, and evaluation costs. The camera that we will be using is the ERAU-HD25. This actually comes with 2 cameras, one with a 720 pixel camera, and the other one is a FLIR 640 pixel camera. This allows us to spot any leaks in the pipelines more easily. Next, I'll be going over the flight test aircraft cost. We broke it down into the electronic package and then the materials cost. This is the electronics that we'll be buying next year, next semester. It includes the transmitter system, the battery, servos, and the engine. The total comes to about $2,100. When we include the material costs that were covered by Katie earlier, the total of the prototype cost comes to $5,100. Now I will be going over the risks that this project has. We came up with several risks as a group, and you can't see the colors very well, but the top 3 risks are cost risks. The next 4 are the schedule risks, and the last 4 are technical risks. We plotted these risks on a PF versus CF graph. The PF is the probability of failure, and CF is the severity of the consequence. Our top 2 risks are both cost over the summer. Next, our second highest risk is poor manufacturability. In order to lower remaking parts and spending extra money, we'll be consulting the machinist and practicing manufacturing parts before we apply them to the final prototype. Now I'll give you a program performance update. This is our spend profile, so the cost accumulation for the semester. We spent about $200,000. The orange dots represent key deliverable dates. The first one's the SRR, the second one's the CDR, then the IDR, and most recently the TDP. These costs and hours are broken down into 4 different sections, where the engineering technical hours are the largest portion of our cost. Our estimated cost at the CDR was $328,000, but we only ended up spending $200,000. And the average hours per week is 130.15. So let me explain these pie charts a little more. The engineering and technical hours is where we did our research and calculations. The second biggest is professional development, which were class hours. The administrative hours, which is where we're documenting our work, and the engineering management hours were spent planning this project. So this is our schedule. The first half, we're given the request for proposal on January 14th, and we responded with an SRR, which stands for Systems Requirements Review. And then we narrowed down our design for the CDR. Using the feedback from CDR, we fine-tuned our design to the IDR. And the last portion of the semester was documenting our work and writing up test plans for the following semester. These are our future plans and recommendations. Our endurance is only 6.2, where the requirement was 6 hours. So we're planning to increase the endurance and revisiting the fuel tank size and the propeller selection. We are going to revisit the tail configuration to make manufacturability easier. For next semester, we will be constructing the prototype and running the wind tunnel test, the engine test, and flight performance test. In conclusion, our aircraft meets all the RFP requirements. It has a range of 6.2 hours, and an endurance of 6.2 hours, a range of 370 miles. It can be disassembled to fit into an 8-foot truck bed, a takeoff weight under 55 pounds, and a payload weight under 10 pounds. All our calculations have taken into account the 10% hot day conditions, and it is a cheaper alternative to the Cessna 172. Thank you for listening. Any questions?
Looks like it might be low, but I'm not know
found in Raymer's book. So we think it is for an estimation for UAVs. And so the variables are defined up there. And the H's are all the hours, and we multiply by the rates. And the rates are actually taken from professor's rate from the class at what rate they assign for each of those tasks.
I mean, one of the things if I were doing one of these, one of the things I would do on something as important as the cost is you just look at what's available there for something similar, is this in the ballpark, you know?
Because we looked at the Boeing Scan Eagle, and we know that it's under $100,000, and the Penguin B is also around $100,000. So that's why we decided that this was a good estimate.
Yeah.
But we'll look into
Yeah.
the estimation.
The Raymer's models are, I don't know, current, that's kind of, I know he's kind of the standard, but does it still apply for these kind of new? That's a good question. I'm not sure.
Because usually the Rand 4 method is very popular for bigger aircraft, and this one was listed as an estimate just for UAVs, and I think they collected the data based on previous historical data.
So I also really like the trade study, show what you did, that's really good. I had specific questions on the ground section. So, for example, if you look at aircraft efficiency, which I think is somewhere around there, was there a specific goal in mind? I mean, you show a nice curve,
Yeah.
but I don't know what, based on just looking at it, I don't know if you met your objective or not.
Well, we do because we meet our requirements of the range and endurance. But this is just how to show you what the efficiency is in our home.
Okay, but you have in your own mind, like, gee, if my efficiency is like 0.7, it's really,
Oh, maybe that working online.
yeah, it just says,
Yeah.
it says something like, it's some
Yeah.
idea of what you were shooting for.
The one, to be honest, as high as possible. Where I tried to shoot the highest at was the wing. That's why we estimated a efficiency of about 94% due to the high aspect ratio. You know, but that goes down because of the body and all the other components on the plane that
So
don't
maybe,
contribute to that.
so maybe you can answer that question might be to relate K and
Yes, exactly.
right? And I know you've got a slide on that that relates K versus Oswald's efficiency factor.
Yeah.
Now, the kid is looking at that?
Yes.
Yeah, yes.
Okay, I got that part, but yeah, that relationship was missing. That's kind of what Roger's trying to. Where did you get E?
I see it in the other package, you not have here.
The relationship between K and E.
Yes.
Well, E is 1 over pi E, pi
Put it on the board. Put
Pi
it on the
K.
board. Put it on the board. Be an instructor. Put it on the board. You gotta show us.
You didn't think you were going to get an education today, did you?
No, I did actually. I'm thinking, well, that's what I get.
Right, yeah.
So pretty much solving by the efficiency factor to switch these two. That's how I got the
And AR is.
aspect ratio, which is the B squared, which is the wingspan squared over the platform area of the wing.
Okay, and one more question on aerospace.
Yeah.
So, static stability assessment, kind of went through that quickly. Could you just
Yeah.
kind of recap real quick? What are the main takeaways that we want someone to take away from this chart?
No.
Was that
37. 37.
Yes.
Oh.
Slide 37. You can so a chart with this many numbers on it, you kind of want to maybe lead the audience as to where you want them to look. I kind of lost track.
Okay. What do you want me to explain?
Just what is the main takeaway you want someone to take away from this chart? If you only have 10 seconds to explain to someone, what would you say, or 20 seconds? What do you want them to know?
The sky clouds from the third column to the left. That's for our aircraft.
Right?
And in order for the aircraft to be stable, it needs to meet those criteria. And they do. So the aircraft is statically stable. That's just the main thing.
But the one in the middle is the optimal range.
It's just a typical range for
Typical range.
historically the ranges for the subsonic aircraft.
And how confident are you you're going to meet these?
How confident?
That's a loaded
Estimates.
question. Wait the fifth.
So,
We'll be doing flight tests next semester, so that way we can verify these numbers.
good.
One, very good.
Yeah. Before you leave that slide, things, Rob, are you going to move somewhere else on this one?
Go, keep going.
All right. So there's one parameter that you're outside the recommended range.
Yes.
You glossed over that really quickly. That's the one that bugs me the most. What are you going to do about it? Is it a big deal or not? And if not, or if it is, what are you going to do about it?
I asked Dr. Bordigman about it, and he recommends that doing roll and
Yeah, so let's describe what that parameter is. Go into detail and CL data.
it's like an airplane somewhere. You can see our airplane. So, do you want me to just go over all the subscript channels?
Go ahead. You did a great tutorial with the IDR.
So the coefficient L stands for roll. So if the aircraft was going that way, it's your roll. And the beta is what is called the side-slip angle. So if you have some incoming velocity, like that. So since there's a vertical right here, and if you apply a force right here, which is in our case a side-slip, you will have, we define using the right-hand rule. This is positive, but then if it's going this way, it's negative. So that means with the beta, you're gonna push the vertical tail, so it's gonna have a negative moment. Does that make sense? But because it is, you see that for the typical range is slightly greater in magnitudes, but that's because for our aircrafts, there's something called a wing dipole, it's like that, and there's a wing sweep, it's like that. So those are what contributes greatly for CL beta. But since we don't have neither of those, that is slightly small.
This is why I asked you how confident you are. So what is your uncertainty in that number? Could it actually be maybe 0.08 and you just see if there's a certain amount of uncertainty in your calculation?
Lots of assumptions in there. Calculation, because it's a very long process to get to that value.
You'll get aero data anyway.
Yes.
I have an aero-related question. I noticed that for both models, for both groups that presented, the nose of the vehicle was semi-cancer.
Yeah.
Why did you guys try to streamline it?
First of all, we're also focusing on how easy it was to build. So by finding a hemisphere, which is pretty much found at, we can use a styrofoam from Michael's or something. So it was easy to build. That was the main purpose of that.
Because I did hear the other group say that they were going to try to add vortex generators to account for the flow separation. It just seems like it would be an easier way to, fix the potential drag increase due to that nose.
Yeah.
You can still buy a piece of foam from Michael's and streamline it.
That's true, we could sand it. We could sand it and make it a lunar shape.
So there's nothing forcing you to have that type of taste.
Exactly. Yeah, true. Thank you. Any other questions?
I noted that it said many of the parts of the plane are going to be detachable. What kind of structural analysis will you be doing to ensure that they'll be sound?
That's out of our scope of the prelim design, so we'll be doing all that next semester in detail.
Well, I think the question is, yeah, you didn't do anything this semester, but what will you do? What do you think you will be doing in the next semester?
So since everything is going to be detachable from our aircraft, obviously we're going to have to beef up all the structure where it actually separates. So on each half of the wing where it separates, obviously we're going to have ribs and spars to just, strengthen it a little bit. It is going to be detachable. That does seem risky, but we need this in order to fit our constraint of fitting an 8-foot truck bed. It can also be noted, like the boom, also there's no structure around that, only because it is outside the scope of this class. That's something we're going to look at in detail next semester.
I think that particular part of the design, the attachment of the wing there, I like the detail that you guys went into with the design, by the way. That was really good. Yeah, I think that's a risk area, and that looks like a tough joint to be rigid. And
Right. We have done some discussion. We're thinking about the boom that goes into the wing, extending it farther. So there are 2 spars that actually do pass through it, just for a little more structural rigidity. Any other questions?
I've got one question on slide 10, the constraint analysis. You had one line on there that I didn't see in the previous presentation, and I think you guys can tell me. It's the line that rolls up and then kind of keeps around 2 PSF wing loading, and then it drops off. What is that line? Yep. And what does that maneuver consist of?
3.5.
3.5 watt. For what kind of maneuver is that?
I guess steady level.
Okay, got it. So now the RFP, I think, had a maneuver requirement of 2 Gs. Okay, so
Yes.
tell me why you guys selected a 3.5 G turn.
We don't.
Okay.
Well, systems engineering not answer my question, so we'll hand that back.
Yeah, we all decided on the 3G. It's not about my decision.
Yeah, right.
That would increase our margin. So if that way we would have an increased wing loading, so we would have a better margin, if we have a bigger wing.
Perfectly acceptable answer. Okay, good. Okay, great.
Yeah. Oh. Go ahead.
Sorry, on slide 40, I get what you did, but I don't understand again what was your goal here? Did you just say, okay, I calculated it, we're good enough, or did you have a specific? I think earlier you stated what your goal was in terms of kickoff landing distance.
Right.
But I guess the RFP says 500. Okay, sorry, I missed that.
Okay.
So you mentioned right?
Yes, that's the.
I have one last question on the, I probably missed this too, on the estimated total cost. There's no engine listed there that I recall. And I guess the engine you don't have to pay for it.
It is actually accounted for in the model. I can show you. So the engine is accounted for the C sub ENG and the N sub ENG. That's the cost times the number of engines per unit.
Where do you folks start on that? But by the original structure making out of plywood, are you going to figure out what plywood they get? Because they don't all weigh the same, right? And then thicknesses.
So for the formers and the firewall, it's going to be made of 1/4-inch plywood. As for all the payload platforms, they're 1/4-inch plywood. And it's just hobby grade, like what to make RC planes out of.
Okay, so is that normally like balsa? Or is it, it's not pine, right?
I don't think it's pine. I'm not too sure what exactly it is, but it's definitely not balsa either. That's too lightweight.
Yeah, so it's gonna be what is normally used, right?
What is normally used, yes.
Yeah, that wasn't clear, so I was looking at it like, okay, I don't think I saw thickness. And then I see the material on the whip.
I just stated the material. I didn't state the thickness, but I'm glad you
Oh,
asked.
it's just a plywood, okay.
Yes.
Fine, but- Yeah, if you would have thrown that in, maybe just like, yeah, we're using something, so we're using.
Right.
But several days.
See, question on slide 15, on your trade study of electric versus gas, your energy source weight here was quoted at 20 pounds, yet your competition quoted a battery weight of 280 pounds. How did you guys come with such a wide variation in battery weight?
I just used the equations from the electrical engineering class. Just the power is P is IV, and you just calculated using that.
So your power density is probably a key part of that calculation, right?
Yes.
Could you go back and verify that with the battery supplier?
I believe when I did the calculations, I was actually looking at a battery that would work, and the biggest battery I found were that were already manufactured were 10,000 milliamp hours, I believe. So we would need 9 or 20 of them each, and they all weigh a pound. So that's how I found the battery weight.
Okay.
But I had hand calculations, not in reference.
Okay.
Yeah, I'm sorry.
Just wanted to know if you guys collaborated with the other team on that calculation also, because there are really big difference in numbers there. So. Okay.
I have a couple of questions. So you mentioned using a GPS. What other electrical components are you planning to implement in your design?
We actually have a list of components. Right here. And do you want to just put that
I think this is more for the production aircraft, which we have in the references. So all of the payload that goes inside of our aircraft was given to us by El Paso Natural Gas. It's not really within our control to change it, but in the references. But we do have a list of things that are going to go in it as well. It's a GPS as well as an antenna for it. We have power conditioning units, just everything to power it and operate it as given to us by our customer.
I have another question. So, what type of data will your GPS collect? Because you mentioned that it's going to be just for you guys to know where it is at.
Right.
So what, is there going to be another type of data that it's going to collect?
That's not really within the scope of our project. Our main concern with the GPS is just to be able to tell where the aircraft is, and if there is something wrong with the pipeline, to be able to flag that location so we know where to come back to.
And are you guys going to implement some type of software into the GPS?
Once again, out of the scope of our project,
Okay.
we design the aircraft, the customer gives us our internals.
Oh, correct. Okay. And also, I just have some suggestions for presenting. What I've learned from presenting is having your, when you transition from this team member to this team member, it seems to flow a little bit better when we say, oh, so now this person is going to talk about this, and that. So that way we expect what that person is going to be talking about.
Right.
And I would suggest a laser pointer too, because I know that the screen is super high, so maybe have a laser pointer to point out what you're talking about, or where you want us to
explain the graphs too.
Exactly. So if you have some type of laser pointer, it would be fantastic.
Thank you for the suggestion. Any other questions?
Okay, thank you all for your time today. I especially thank the panelists who traveled from Tucson and Phoenix. I really appreciate you guys. Thank you for being here. And you guys did a great job. Both teams, outstanding work. Honestly, I thought that your group couldn't be topped, but I think you guys did a really good job too. So I mean, I was very impressed with what you did. Now, Shelly, you need to go home and go to sleep. You probably haven't slept. I know you haven't slept last night. I don't know how little sleep you've had. So anyway, get some rest. Well deserved. And everybody, you guys, I know you did a great job. So get some rest, and we'll see you back. Yes.